Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we'll be going through the next topic in the series of thermophysics, which is the transfer of thermal energy. So in this topic, most of the stuff that are covered in this topic, you have already seen them in your lower sec, your sec 2 topic on the same title, in fact. Alright, so there's really nothing much new here, but except we're going to delve a little bit deeper into the applications portion as well as the mechanism of each of the three modes of thermal transfer, which is conduction, convection, and radiation. Right, so without further ado, let's begin. Right, in the first section, we talk about this term called thermal equilibrium. Right, thermal equilibrium basically just means same temperature. So you might want to write down over here, thermal equilibrium. The word equilibrium means no further change. No further changes. So you learn in chapter 5, right? Turning effects of forces. When an object is in rotational equilibrium, it's no longer rotating. So the word equilibrium here also means no changes, right? But here we're talking about for the purpose of thermal energy or temperature, right? So yeah, so the words equilibrium here just means no further changes. Okay, so heat energy or thermal energy rather is always transferring from regions of high temperature to regions of low temperature. So this is something that you already know in your lower sec. Alright, so for example, if I have two objects here, one at 40 degrees Celsius and one in 20, and they are in thermal contact, right, literally physically contacting each other. So in the absence of any other heat sources from the outside, right? So assume that this thing is isolated from the surrounding, then what you will see is that, okay, energy is going to be transferred from the one that's higher temperature 40 to the one that is lower temperature, which is 20, in this way, right? So the heat energy is going to be transferred in this way. So again, thermal energy is always transferred from regions of high temperature to regions of low temperature. So in this case, will it go on forever and ever? Will the thermal energy keep transferring from the box at the top to the one at the bottom? The answer is no, because after some time you realize that they achieve the same temperature, right? And that is what we call thermal equilibrium, right? So when that happens, right, there's no more region of higher temperature, no more region of lower temperature, both are at the same temperature, then you achieve thermal equilibrium because they are at the same temperature. Okay, now this number 30-30 is an average of 40 and 20, but most of the time it's not like this. They will be at the same temperature, but it will not be 30. Most of the time it's not 30. It is only exactly 30 if and only if that they are the same temperature, same material, they're exactly the same mass, exactly the same thing, and there's no heat lost or gain from the surrounding air, right? So this number 30 will not be true most of the time, but the two numbers will be the same. So you don't have to know what exactly is the number. Yeah, so you don't have to worry. Just know that heat transfer will stop when the temperatures are the same. And this is true that when I say that thermal energy is transferred from regions of high temperature to low temperature, this is true for all three modes of heat transfer. Alright, when we talk about conduction, convection, and radiation later, you will see that it is all from regions of high temperature to regions of low temperature. Okay, so yeah, so this is what I've been saying just now. In which direction? Right, so it's always from regions of higher temperature to regions of lower temperature, not amount of thermal energy. We're not looking at the amount of thermal energy, we're looking at the temperature itself. Okay, essentially from hot to cold places. So will it go on forever and ever, or will it stop? No, answer is it will continue flowing until you reach the same temperature. Right, the two regions reach the same temperature. Yeah, so this is so we can take a note at the side. Note that this is true for all three modes: conduction, convection, and thermal radiation. So this is true for all three modes. I don't care which mode I'm talking about. This is always true. High temperature to low temperature. Okay, right. Let's look at this example here. Thermal energy. Sorry, a small metal cube, okay, with temperature of 50 degrees Celsius is placed in thermal contact with a larger cube that has temperature of 30. In which direction will the thermal energy flow? So this is kind of like a trick, right? It doesn't matter the size, it doesn't matter the mass of the object. Thermal energy will always flow from higher temperature to lower temperature. So this is the answer over here. Pause the video to take it down. Okay, let's move on here. Right, so just now we talked about the direction of flow of thermal energy and thermal equilibrium. We now move into the main crux of this chapter, which is the three modes of thermal transfer. There are conduction, convection, and radiation, and we begin with the very first one called conduction. So you have to recall what is the definition. You have to explain what is conduction at the atomic level, and explain why metals are better conductors of thermal energy than non-metals. Okay, so let's begin. So when we talk about conduction, okay, the definition important. Okay, conduction is the transfer of thermal energy through a medium without any flow of the medium. Alright, so first of all, let's break it down, right? What does it mean by medium? The word medium here refers to any material. It can be solid, liquid, or gas. So I write down there S, L, G, solid, liquid, or gas. Any material, right? Air is also a medium, right? So long as there's matter, it is considered as a medium through which the thermal energy is being transferred, right? Okay, so this conduction requires a medium. That's number one. It requires a medium, and the medium does not flow. And what does it mean by flowing? Well, I can't really explain as of now, but you will see what is flow when we talk about convection, right? So you might want to recall a little bit from your lower sec knowledge. What is convection look like? What does convection look like? We will see it later, but if you can recall, then you'll understand that convection is actually a flow of the medium, while in this case conduction, there is no flow at all. Okay, so the mechanism of conduction, this is what you have to memorize. You have to know how to write, right? Explain. So the question for this part will be, describe how conduction occurs in a substance or a medium. Essentially how conduction works. The key thing here is about collision of particles. Okay, so let's go through one by one. So when we have one end of the solid, let's say I have a solid over here, right? A rod, metal rod. Okay, and I hit on one side, on the left hand side. In this case, when I hit on the left hand side, number one, the particles near to the flame will gain the thermal energy first, right? Because they're close by virtue of them being closer to the flame. Yeah. So when number one, so the particles get heated and they vibrate more vigorously. So this is chapter 7, right? The previous topic, right? When particles gain thermal energy, they gain in the internal kinetic energy. So they vibrate more vigorously, right? Then after that, what happens? How does the the thermal energy get transferred from one end to the other end of the rod? Well, it's by collision, right? So the particles that are nearer to the flame, once they start vibrating more vigorously, they will tend to collide into the neighboring particle, in this case the second row particles. Yeah, so by colliding, effectively what happens is they are transferring the energy to the second row over here, right? So by colliding, they're transferring the energy in terms of internal kinetic, right? So now that the second row receive some form of energy, they vibrate more vigorously as well, right? So once they vibrate more vigorously, okay, it's like a domino effect, right? The the story continues. They collide with the third row and so on and so forth. So the particles transfer energy to the next particle in line by colliding, and this is the keyword over here, is by collision, colliding with them. So therefore, the thermal energy that is from the flame is being transferred to subsequent rows of particles in terms of the internal kinetic store. Okay? Yeah. So eventually, particles on the right hand side of the rod will also receive energy once their neighbors collide with them and transfer the energy. Yeah. So this is how conduction happens at the microscopic or the particle level. Yeah. Right, so we say that there's no flow of medium because the transfer is only done by colliding. There is no need for the particles to make its way all the way to the other end of the rod or the solid in this case to pass on the energy. There's no need for the particles to move away from their position. So it can happen, right, without them flowing, without them moving from one end to the other end, one point to another point. This is why conduction is called is described as without the flow of the medium. But of course, to get a better picture, you need to see what convection is about. Alright, next up. So this is a video that you can view on your own to help you to visualize, right? So I will not show over here. Okay, next up. Comparing the same material, right? If I'm talking about the same substance, solid, liquid or gas, which one conducts thermal energy faster? Or rather, I can rephrase the question saying that which state of matter is best in transferring thermal energy via conduction? And the answer here is solid, okay, compared to gas, which is very, very slow. Why is that so? Because you have to go back to the mechanism to see that conduction effectively is the collision of the particles, right? It's due to the collision of particles. So if you compare how closely packed the particles are, solids, if you recall from previous chapter, they are very, very closely packed. So it's very easy for them to bump into each other, to collide with each other. As compared to gas, they hardly meet each other physically. So the rate of collision between particles in gas is significantly slower than solid. So this is why conduction is best in solids, right? So the key thing here is particles in solid are closely packed together. So as a result, they collide with each other more frequently. Okay, so they collide with each other more frequently. This increases the rate of conduction, of energy transfer through conduction, yeah? Okay, next up. Okay, in this chapter, you will realize that there is no calculation, yippee, yeah? But there's a whole bunch of writing to do, a lot of explanation to do. And you know that in science, by experience, you should know, if you don't use the correct keywords, I shouldn't be saying that, but it's the reality. If you use the wrong keywords, or if your explanation is not very, very sharp, you tend to lose some marks here and there. Alright, so let's learn to use the proper keywords for each of the three modes of thermal transfer, right? So for conduction, in particular conduction, we talk about conductor and insulator. This is something that you already know. Just need to note that when we talk about conductor, please include the phrase of thermal energy over here, because we recall that they are good conductors of electricity as well. So we want to distinguish between electrical conductors and thermal conductors. Alright, so these are the qualifier here of thermal energy is important. Okay, so we have two words here, conductors and insulators. How are they related to each other? Well, you should know by now that they're opposites of each other, right? So if you're a good conductor, you are a poor insulator. If you're a good insulator, you're a poor conductor. So they are opposites, right? One good, then the other one will be a poor, right? So the key here is, like as I will emphasize again, when in questions, when you explain thermal transfer, you must always tell the examiner which mode of thermal transfer you're talking about. Okay, in this case, if we're using the concept of conduction to explain, then please write down the words here via conduction. Via means through the mode of conduction. So via conduction, via convection, or via radiation. So you're telling the examiner very clearly that I know that in that special case, in the question, we are talking about conduction over here. Okay, so which mode of heat transfer, please list down very clearly in your answers. Okay, so conductor and insulator, and this is only used for conduction only. If we talk about radiation, we do not use the word conductor or insulator, because it's for conduction, right? So I'll emphasize that later. Okay, so this part here is something that you need to know. We learned from primary school that metals are better conductors in general of thermal energy than non-metals, right? But we never knew why that's the case. We just know that this is a fact. Okay, so here we're gonna know why is that the case. Right, I don't know whether you learn in chemistry, but for metals, the way that the atoms are bonded to each other is not covalent, it's not ionic, but rather this type of bonding called metallic bonding, right? So the way that they describe in chemistry this metallic bonding is a sea of is the positive ions, which is the metal ions, okay, surrounded by a sea of delocalized mobile electrons. So the keyword here is delocalized, and maybe you might want to add in delocalized and mobile. The word mobile here suggests that they are free to move. Alright, so they are free to move about throughout the whole metal. Unlike covalent bonding, where the electrons are stuck, so-called stuck, right, in the bonding, or at least tight bounded to the atoms themselves, these electrons in the metals, they are mobile, they are free to move about, they are not attached to any of the atoms, or rather the ions. Yeah, so how does that help, right? Okay, how does that help? So bear in mind that with the without the mobile electrons first, let's talk about non-metals. Yeah, so the mechanism for conduction for non-metals is the usual collision of particles as I've described earlier, right? So just collision of the neighboring particles, thereby transferring energy, internal kinetic energy, which causes the neighboring particles to vibrate more vigorously. So this is the usual mode, the usual mechanism for conduction. But in metals, you also have that. The ions over here, they are also capable of vibrating and colliding with neighboring ions, positive ions, the cations. But in addition, you also have this free electron, these mobile electrons. What they can do is they can move about freely. So they can move from one end of the of the metal, and to the other end, and collide with some of the electrons or ions or cations over there, thereby transferring the internal kinetic energy. So it's also by collision, same thing, but now for metals you have extra players here. You have the free moving mobile electrons that can help to carry the internal kinetic energy to the other end of the metal and collide with the ions there, right? Thereby speeding up the process, because now you have two mechanisms. You have two mechanisms over here instead of just one. Okay, let's move on. So all these applications, I leave it up to you to read it itself. But the way that you explain this type of questions, which is quite a lot in exams, basically they'll show you an item that is specially designed to either increase or decrease the rate of heat transfer, and will ask you what is either point out to you the special design and ask you why it works, or ask you to figure out, right, what is so special about the design, and then figure out how it works. Okay, so in this case, a quick simple example is that, okay, saucepans, your cooking pots and pans, they're usually made of metals, right? This one you know is because they are good conductors of heat energy, so therefore the thermal energy from the heat source can be transferred to the content inside the saucepan or the pot quickly, right? So this is one way. Okay, next. So other examples like the handle of a saucepan, you know, is either rubber or plastic because they're poor conductors or good insulators, which will prevent then the user's hand from being burnt, so on and so forth. Yeah, so also typical questions would involve you identifying pockets of air. So if you see any things that traps air inside, like your woolen clothes, okay, or cotton, thick cotton, or animal fur for that purpose, these things, if they trap air, chances are they are trying to reduce heat transfer via conduction. Because why is that so? Because of this, right? Air is a gas. They are poor conductors in general. Okay, so yeah, like I said just now, the the animal fur, penguins. I don't know why the word's not appearing, but yeah. So the key here is, maybe I'll wait for the words to pop out later. But the feathers, they trap air, right? So it's the same concept here, right? Here you go. Okay, so there's trapped air between the layers of feathers. So this is an air is a good insulator of heat or thermal energy by virtue that they are gases. So this prevents heat energy from escaping the body of the penguin, thereby keeping it warm. Okay, so you can pause the video here to take it down, otherwise I'll move on. Right, so now we move on to convection, which is the second mode out of the three thermal transfer mode of thermal transfer. So the description, the definition here, again, anything in between two lines, please get memorized. So convection is the transfer of thermal energy via the movement of current in the fluid. So now we talk about flow. Just now in conduction, we say that there is no flow of the medium. So in this case now, convection, we are talking about a flow. There is a flow now, and that flow is called convection current. Convection current, yeah? Okay, so you may recall that a convection current looks like this. If the heat source is right smack at the center. Okay, I don't know why the software is a bit weird. Yeah, here we go. So if the heat source is right smack at the center, you recall that the convection current looks like this, sort of like two butterflies, one to the left, one to the right, completely symmetrical, if the heat source is right smack at the center. Okay, so how does it work, right? How come there is a convection current? So we go by step. Again, this is the mechanism. You need to remember how to explain this. So you gotta memorize the mechanism. How does it work? Yeah. Okay. So first up, when the water at the bottom is being heated, is closest to the heat source. So it's gonna get heated up first. Okay. So when water is heated, you know that anything that gets heated, it expands. Alright, and most of the substances, yeah, not all, but most of substances, when they get heated, they expand. So what does expansion actually means? Expansion also means that the volume increases, you see. Okay, because the size expands. So when that happens, it's related to the density now. Because density is mass over volume, so you can see that when volume goes up, density will go down. So as a result of the expansion, the density of the water near the bottom, or rather near the heat source, its density will decrease, you see. Right. So density is decreased, as a result it rises, because you recall from Sec 1 science that less dense substance floats above more dense substances. Okay, so the density of the water near the heat source, this region, is lesser than the rest. So as a result, it's gonna rise. It's gonna float above the rest of the water. So when it rises, it will leave behind an empty space, right? This yellow region here that I highlight with the highlighter, once the hot water here rises, it will leave behind an empty space. So no choice. What you observe is that the water from the rest of the water, right, that is not as hot, will come in to replace. So we call it cold water sinks to the bottom. Actually, it's coming in from the side. It's coming in from the side, right? So what happens then is that when the colder water comes in, as indicated by the blue arrow, they come in, is now in close contact with the heat source. They themselves will get heated up as well, just like the hot water from earlier. So as a result, they become hot themselves, and they also start to rise. And then other cold water will start coming to replace them. So this will happen again and again. It forms a cycle. The pattern will repeat itself to form a cycle, which looks like the red and blue arrow that I draw over here. So this cycle is what we call a convection current. Yeah, convection current. Okay, so one thing to note, that just now in conduction, we see that it can happen in all three states of matter: solid, liquid, and gas. Just that it's lower in gases. Over here in convection, it's not so straightforward, because it can get it is only applicable to liquids and gases, which is what we call fluids. Okay, let's wait for the words to pop out again. I don't know what happened to my iPad today. But yeah, convection can only happen in liquids and gases, but not solids. Okay, so this is what we call fluids. Liquids and gases are together called fluids. Okay, so why is that so? This is something that you need to know how to explain as well. Now, remember that convection involves the flow of the particles of the substance itself, which is essentially is the particles, right? In order for the particles to flow, or rather, in order for the medium to flow, the particles must be free to move about. Okay, so you recall from chapter 7, right? We go back to the picture over here. Which of the three states are the particles free to move about? Definitely liquid and gases, not solids, right? So you recall that in solids, the particles are held at fixed positions. Okay, so as a result, only liquids and gases can transfer heat energy via convection. Right, so just now when we talk about conduction, we said that there is no flow of the medium. Yeah, so in this case here in convection, there is a flow in the form of a convection current. Okay, right, so this is another video for you to help you to visualize how convection current looks like. But typically when we talk about applications examples here, there are two ways in general to create a convection current. Either you heat a fluid, which is liquid or gas, at the bottom. You create a convection current like what we see just now. This is a heating convection current. Or if I want to cool stuff, you cool at the top. That means the cooling source should be at the top. Okay, so why is that so? This will create a convection current as well, just that it is a cooling convection current, not a heating convection current. So this is why you realize that your ice compartment in your fridge, in your refrigerator, usually is found at the top of the refrigerator, usually. Why is that so? Because when a freezing unit is cooler, it creates a convection current that looks, actually this arrow is wrong. It looks like, let me just quickly draw it. It looks like this. Okay, it should be symmetrical. I'm sorry. Yeah, it's very hard to draw on the iPad over here, but it should be symmetrical. Okay, so having a cooling unit at the top will create a convection current that effectively helps to cool the rest of the items in the fridge faster. Okay, so here we go. Okay, there are two ways to set a convection current. One is to heat at the bottom, and the other one is to cool at the top. And you're invited to think about what if we heat the fluid at the top or we cool at the bottom. Is there convection current going to be formed? Think about it. Okay, but in general, when we look at which states can conduction and convection and radiation happen, right? This is a summary of the table. We have not discussed about radiation yet, which is the next section, but you may just take this down first. Okay, do note that for conduction and convection, because they require a medium, okay, they necessitate a material in between the 2 points of transfer in order for them to happen. They cannot happen in vacuum. Remember, vacuum is absolutely no material, not even air. So in outer space, where there is no air at all, nothing, conduction and convection cannot happen, but radiation can. Alright, so we come to that later. Alright, let's move on to the next page over here. Okay, so depending on where you put the heat source, the convection current is going to look differently. Okay, let's look at the very first case. When the heat source is placed at the center, in the middle bottom of the fluid, then you have a two butterfly kind of a scenario, one to the left, one to the right. Okay, over here the way I draw is not very symmetrical, but you should draw it symmetrically, and it should cover the entire tank. So what do I mean by that? I'll show you a negative example. Red color. The black one is good. What is not good is red, like this. They're kind of symmetrical, but you realize that they did not reach the end of the whole fluid, the water tank. Almost as if saying that convection current only happens in the middle. So this is absolutely wrong. Okay, so you should draw your convection current such that it reaches the end of the container as much as possible. Right, so if it's heated at the center, you get 2 butterflies. But if it's heated on one side, you only get 1 butterfly. So again, it should reach the ends of the container and not just a small loop near the flame. Okay, now we come to the tricky part, right? What if I'm heating the fluid at the top, which is what I invited you to think about earlier? In that case, there is no convection current here. Why? Let's think about it. When you heat the fluid at the top, the region here gets hot, right? The water at the top gets hot. Well, we recall that hot fluids, hot water, or hot air will rise, you see, okay, compared to the cold ones. So, but it's already at the top. It's already at the top. So there is no room for it to rise further. Well, on the other hand, the colder water at the bottom remains at the bottom. So hot water remains at the top, colder water remains at the bottom. There is no flow. There is no convection current in this special case. So nobody heats water source from the top. They always heat it from the bottom. Okay, so the next question is, eventually, will the cold water at the bottom still heat up? The answer is yes, definitely yes. But it's not through convection. Rather, it's through conduction. Right? Since there is no convection current, the only way for thermal energy from the flame to reach the bottom of the water in this case will be through conduction. But we recall that water or fluids are very, very poor in conducting thermal energy. So therefore, this is a very slow process. That's why nobody ever does that, which is ridiculous. Alright, we come to the last of the 3 modes of thermal transfer, which is radiation, thermal radiation. Okay, so this is the most poorly understood out of the 3 in general for students, because it's very hard to see. I cannot show you radiation. I cannot show you thermal radiation because it's not visible to the eyes. Okay, you you need special sorry. Okay, you need special cameras and devices to detect. You see? Okay, so what exactly is thermal radiation? So thermal radiation effectively is the transfer of heat in the form of this thing called infrared wave. You must have heard of this word infrared somewhere. In fact, in the chapter 5 of Sec 1, light, ray model of light, in the very last part of the chapter, we cover this thing called infrared. Okay, so there are waves that we cannot see with our eyes. They behave like the light that we can see. They behave like the usual light that we can see. Alright, they are in charge of transferring thermal energy. Yeah, so for thermal radiation, the thermal energy is being transferred through this waves called infrared, and it can happen without a medium, without a material. So radiation, like I said earlier, is one of the only only one out of the 3 modes of thermal transfer that can happen without a material in between, and it can happen in vacuum. So standard example is when we receive thermal energy from the sun, in between Earth and the sun is empty space, is vacuum. So how can we still receive thermal energy? It's through infrared, through thermal radiation. Yeah, so recall that in a vacuum, conduction and convection cannot occur. Therefore, only thermal radiation can happen. Okay, so it's in the form of waves. Yeah, so in fact, any object that is hotter at a higher temperature than the surrounding will emit thermal radiation, infrared waves. So recall at the very beginning of this chapter, we say that thermal energy is always transferred from regions of high temperature to low temperature. And let me reiterate that it is true for all 3 modes of thermal transfer, including this thermal radiation. So when you have an object that is of higher temperature than the surrounding, it will start to radiate heat away. So does your body. Alright, your body temperature is approximately 36 to 37 under normal conditions, and your surrounding air is, at least in Singapore, it's about 30, 31, 30, around there. Right? So your body is at a higher temperature than the surrounding. Like it or not, you are constantly radiating thermal energy away to the surrounding. Okay, just that we cannot see these waves, like I said earlier. So this is something, a video for you to visualize. Okay, now when we talk about radiation, there are three keywords to use. Remember, we do not use conductor and insulator. That is for conduction. For radiation, for thermal radiation, we have three different keywords, which is absorber, reflector, and emitter. Let's go through one by one. Absorber means to take in, right? Absorb. You absorb nutrients. You take in the nutrients. So a good absorber of thermal radiation is good at taking in heat via thermal radiation. Okay, so you see, again, which mode of thermal transfer are we talking about? We must state it very clearly. So in this case, absorb thermal energy via radiation. Okay. Reflector, just like when I talk about reflector, I always think about mirrors and light. So you recall that a mirror is good at reflecting light, right? And this is your Sec 1 topic. We talk about the law of reflection. Reflect. Right. So same goes for infrared waves as well. They do reflect off surfaces. Sometimes they get absorbed into the material. Sometimes they get reflected off. Right. So when a material reflects the infrared waves, the radiation, they do not absorb it. Very simple, because it bounces off. So the material does not take it in, right? So this is why absorber and reflector, they are opposites of each other. If you absorb, you do not reflect. If you reflect, you do not absorb. Very simple, right? So good reflectors, they absorb thermal energy poorly, again via radiation. So you see, the mode must be very clearly stated. Okay, but they reflect well. They reflect thermal radiation very, very well. Okay? Later we'll see what kind of materials are as such. We come to the last word called emitter. To emit is to release or to give out. Just like this picture over here. This teapot is emitting thermal radiation. It's giving out because it has a high temperature compared to the surrounding. Yeah. So if you are a good absorber, if a material is a good absorber, it is also good at emitting. If a material is poor at emitting, it is poor at absorbing. So they're kind of the same thing, even though the mechanism, the direction is completely opposite. But yeah, a good absorber material will be also a good emitter material. Okay, so emits thermal energy again via thermal radiation. So here comes the next question that I always like to ask. If something is good at absorbing and emitting, when does it absorb? When does it emit? Then, think about it. When does something absorb? When does something emit? Then, since they are going to be good at both, right? Okay, so we go back to the beginning of this chapter again. Right? So, heat transfer always from high temperature to low temperature. So it's very simple. If the temperature is higher than the surrounding, it will emit. If it's lower, which is the blue color ink, if it's at a lower temperature than the surrounding, it will absorb. That's simple, right? So the very first principle, high temperature to low temperature heat transfer, is always true. Always true. Okay, so just now I say some materials are good at absorbing, some are good at reflecting. So what kind of materials are good at what? So the factors affecting rate of transfer of radiation, these are all concerning the surface of the object. Please take note, the factors that I talk about here only concern the surface, which means if I have a box, I'm only concerned about the surface of the box. I'm not concerned about what's going on inside. Okay, so these are the factors that you've already seen in lower sec, so no big deal. The color of the surface, the texture, the temperature, and the surface area. Okay, so again, these are all surface factors. We don't want to talk about surfaces. So black or dark colored surfaces are good at absorbing, good absorbers of thermal radiation. Bright colored ones are poor absorbers and therefore good reflectors. Okay, so when I say fast and slow here, I mean good or poor absorbers of thermal radiation. Okay, alright, so you have dull, which is unpolished, not shiny. Another word for dull is matte, M-A-T-T-E, M-A-T-T-E, matte. So you see some of the cars in on the roads, right? Some of them, most of them are painted. The paint is very shiny, but some of them, they purposely use the dull and unpolished paint. Okay, so it looks matte. It looks different. Yeah. So shiny and polished surfaces are good reflectors. They are very good reflectors. Therefore, they are poor absorbers. Yeah. Okay, and the temperature difference between the object itself and the surrounding matters. The larger the difference in temperature, the faster they either emit or absorb thermal radiation. And last but not least, of course, the surface area in contact with the surrounding. Okay? Okay, so yeah, it is a bad idea to wear dark colored t-shirts on a hot day. Just to take note that in exams we will not play with colors. We will generally just use black, white, or black, silver, or dark and bright colored. We will not play with things like dark yellow or light blue, that kind of thing. And you have to kind of figure out which one is darker than the other. So don't worry about that. Okay. All right. A tale of two cars. So you have two cars that are at the same internal temperature, the air inside is the same at the start, and they are parked under the hot sun. The question is, which one will have hotter air inside after some time? So yeah, the answer is very obvious, the black one, because they are good absorbers of thermal radiation. Pause the video to copy down if you need to. Okay, here comes part 2. Now that they have reached the same hot temperature after being parked outside for some time, they are now moved into the shade to cool down. Which one would cool faster? Which one will have a lower temperature after some time? So the trick here is that, yeah, it's also the black one because they are good emitters. So here the keyword here is emitter, right? Now under the shade, they are emitting. Just now under the hot sun, they are absorbing. So see the difference here, right? So the one that absorbs faster will also emit faster. This is why the black color car will cool down faster in a low temperature surrounding. Roger? Okay, we come to the very last section. Okay, now just now in the previous 3 sections, we learned how the 3 modes of thermal transfer work. That means the mechanism, right? In exams, we can also very often ask you about applications, which is how these 3 modes of thermal transfer, the principles, are being utilized to either speed up or slow down heat transfer. Okay, so when it comes to this type of questions, I have a template for you to answer, okay, which is called purpose, design, and the physics behind. So that means if I give you an object and I ask you, why is it designed in such a way? So first you answer, what is the purpose of the object to begin with? Okay, then you highlight what is the special design. Oh, certain things are made of metal, for example. Certain things are made of plastic. And then you talk about the physics behind. Why is it that that particular object is made of that material? Or why is it designed in such a way? Okay, so if you follow this 3-step process, you would have covered everything. You can be sure to get full marks for your answers. Okay, I give you a simple example just to illustrate. Why is the body of the frying pan made of stainless steel? Okay, let's start with the stainless steel part, right? Purpose. Okay, the purpose of the frying pan is to ensure that the thermal energy from the flame is transferred, is well transferred. Okay, so sorry, my answer here is not full. The purpose of the frying pan is to ensure that the thermal energy from the thermal energy is transferred okay, it's being transferred and hopefully quickly from the flame to the food. So what is the special design here? The design here is that it's made of stainless steel, which is a metal. Okay, and then last but not least, the physics behind. Why metal? Why do you use a steel frying pan? Because it is a good conductor of thermal energy, and then therefore heat from the flame is being transferred to the food faster via conduction. So you see, I need to mention which mode I'm talking about here. Good conductor and then via conduction. So you see the three-step process, the purpose, the design, and the physics behind. Then we look at the handle. Why is it made of plastic? Okay, so the plastic is designed to ensure that, what's the purpose? So that the user's hand doesn't get burnt. The special design here identified is that the handle is made of plastic. And then what's the physics behind? Because plastic is a good insulator or poor conductor, therefore reduces heat transfer from the pan to the hand, again via conduction. Which mode are we talking about here? Okay, good insulator or poor conductor. You choose whichever you want. It's the same. Okay, so the three-step process here: purpose, design, and the science behind, the physics behind. So another example here, the refrigerator. Just now we mentioned that the ice compartment is usually at the top, right? Why is that so? So I'm here using the three-step process to explain. So the purpose is to cool the contents down, the food inside, okay, to cool down faster. Step 2 is to talk about the special design. The freezer compartment is placed at the top because it's colder. So first of all, it's colder than the other parts because it's supposed to make ice, right? Make ice over here. It is placed above the other compartments. So what is the science behind? So you can go ahead and talk about convection current. The cooler air sinks, okay, while the hotter air from the rest of the compartment will rise to the cooling compartment, so on and so forth. So this sets out a convection current. So when you see the word, you see a case whereby obviously it's talking about convection current, please make sure that you have the word convection current in your answer, because usually that's going to carry one of the marks. Okay, so it allows the other compartments to cool down, the components to cool down faster, quickly and efficiently. Okay, so I just want to add on something to step 1. Quickly, or rather efficiently. Okay, quickly and efficiently, up to you. So the design of the fridge to put the freezer compartment at the top is such that they are utilizing the concept of convection to cool down the food inside the fridge faster. Okay, so again, the 3-step process here. So you can use it to apply to a heating case for convection. Why is it that, yes, we always heat a fluid or water from the bottom, right? So the heating coil is always placed at the bottom, never placed at the top. Only idiot would do that. Okay, so why is that so? Again, purpose, design, and the physics behind. I'm writing the 3-step process at the top to help you to structure your answer. But once you kind of get the hang of it, there is no need to list them down in this 3-step process. Just combine everything into an answer. Okay? So pause the video here to take down the answer. I'm going to move on. Alright, the last part here is a very typical example that you'll find in all textbooks for this chapter. Okay, we're talking about the thermal flask, and there are many parts of the thermal flask that are specially crafted, specially designed to reduce heat transfer between the water, the contents inside the thermal flask and the surrounding. So if you are keeping hot liquid, in this case, you want to prevent or reduce heat energy from escaping, right? From moving from the liquid to the surrounding so that it remains hot. On the other hand, if you are keeping cold liquid, then you will want to reduce heat transfer from the outside surrounding into the liquid itself, so to keep it cold, right? So depends on what you're keeping. You have to block both, right? Because the thermal flask can be used to keep either one, supposed to, right? So you effectively you just want to reduce the heat transfer from the outside to the inside, or inside to the outside, right? And there are many special features in this thermal flask aimed at reducing or completely blocking different either of the three modes of thermal transfer. Let's start off with the plastic cap. Plastic insulator of thermal energy. So reduce heat loss to the surrounding or reduce heat gain from the surrounding depending on what liquid you're keeping inside. Alright, via conduction. So again, through or via conduction, very important. So you're telling the examiner that I know we're talking about conduction here. Next, you have silvered surfaces. Okay, so this one, the plastic cap, reduces conduction. So then we have to think about, okay, then there's convection and there's radiation, right? Okay. And actually another thing about plastic cap is that it also prevents convection. Let's write down. Okay, this plastic cap also prevents convection by, how does it prevent? Well, effectively it cuts or prevents the flow of convection current to the outside, okay, to the outside of the thermal flask. So prevents convection by effectively blocking okay, so basically, okay, you can pause and write down. I'm just gonna shift. If I'm looking at a plastic cap here, there's the opening of the mouth of the bottle. If I don't have this plastic cap, what is gonna happen? Think about hot fluid. Okay, it's gonna heat up the air around here. The hot air is gonna rise and move out and escape the thermal flask, thereby causing heat energy to be transferred outwards, okay, away from the liquid. So by having a plastic cap, effectively it cuts the convection current flow outwards, right? It prevents that. So the plastic cap itself has two functions over here. Okay, so this guy reduces, oh, take note, for insulator, we cannot prevent conduction. It is a poor conductor, but doesn't mean it does not conduct at all. So the keyword here very important. We're using the word reducing and not preventing. But as a cap, it can prevent convection because it cuts the flow. So absolutely no flow at all. There's no convection current at all. It can prevent. So there's a difference between preventing and reducing. Later we will see. Okay, so now that we have covered conduction and convection through the plastic cap, how about radiation? Radiation is dealt with by the silver surfaces. Okay, so inside the thermal flask, the lining over here, I use a blue color, this portion here and this portion here, everything inside, right? Basically this part and this part, they are all silvered. Okay, they are covered with a very polished silvery metal. So looking at the word polished silver, right, you probably will have to think about radiation. So they are good reflectors of thermal radiation and then reduces heat loss through radiation, again via radiation, the mode, by reflecting the radiation back to the hot liquid or reflecting the radiation back to the surrounding so that it does not reach the cold liquid inside. So the picture goes like this, right? Let me just quickly erase and then show it to you again. Hot liquid, the heat energy is trying to escape the hot liquid by radiation because it's at a higher temperature. But as the radiation reaches the silver surfaces, the inner walls, they get reflected back. Ta-da, denied. Thou shalt not pass. So therefore, the thermal radiation stays well within the fluid itself, thereby keeping it hot. Okay? So, in this case, you realize that I'm using the word reduces also, not prevent. Okay? These silver surfaces, they are good reflectors, but they are not perfect. They do absorb a little bit as well. So it's not foolproof, it's not 100%. Okay? Something interesting also, in between the two silver surfaces is a layer of vacuum. Right, so we mentioned vacuum earlier. It can effectively block conduction and convection because they require a medium. So only radiation can pass through this layer of vacuum, but it is reduced by the silver surfaces. So let's look at the vacuum itself. Okay, vacuum just means no medium, absence of medium. It can prevent. Okay, so here I'm using the word prevent conduction and convection completely because it is a vacuum. Conduction and convection cannot happen in a vacuum, 0%. Okay, so here I'm using the word prevent. Okay, so not so important is the anti-shock pads. They are usually styrofoam. Styrofoam is a poor conductor of heat. So again, we're dealing with conduction over here. So why is styrofoam a poor conductor of heat? Go back to the previous section about conduction because there are air bubbles inside, traps air, and air is a poor conductor. So sometimes the question may require you to explain a little bit deeper into why this material is a poor conductor. So that would probably give you an extra 1 or 2 marks, okay, depending on the question. Yeah, so this thermal flask is a typical example you can find it in all the textbooks because different parts of it are designed to either reduce or prevent some or one of the 3 modes of thermal radiation, right? So this is a very good example of application where you want to reduce heat transfer from one point to another, and what is done, what are the special designs used, okay, to achieve that purpose. All right, so we're done with this chapter. I hope you learned something. All right, hope to see you back in class. Take care.